Slideshow, play from start. Great. Okay, welcome to our next lecture, lecture 22 on earthquakes. Okay, so the next couple of lectures that I have for you all are chock full with these videos. Click on them in your own time. I'm not going to go through them because there's just too many, but they're really great and they're a really nice addition to these lectures, and I think that they're really helpful and neat too. So go on them, click on them. They're not super long. Any of them are super long, maybe a couple minutes each, and they just really add some nice depth to these lectures. So please go through those in your own time. So next few lectures have a lot of these links in them. Okay, hopefully you can see most of the graphics. Maybe I can move these around. Okay, cool. Okay, so earthquakes, what are they? Earthquakes, the vibration in Earth's lithosphere caused by a sudden release of energy. Okay, and this energy is released in the form of seismic waves that travel through the Earth. So if you remember my ruler analogy, let me grab a ruler, back a few weeks ago, right? You have this ruler here, and this is an analogy for the Earth's crust, right? And I'm building up energy into this ruler as I bend it, right? And if I release, that ruler is going to go back to its original shape, right? So this is called elastic strain, right? You're deforming the rock, but you're not applying that much pressure to it, so it's able to go back to its shape, right? But if I keep pressing on this ruler and I keep pressing and I keep pressing and I keep bending it, I'm building up energy in this ruler, right? If I build up too much energy, this ruler is going to snap, right? And that ruler, when it snaps, is going to release a bunch of energy in the form of seismic waves. Okay, so that is really what an earthquake is doing. When we have these earthquake activities, right? We have this rupture in the Earth's lithosphere that's releasing all of this energy that was built up by this friction. Okay, so keep it moving here. Okay, so most of the earthquakes that we have, they are caused by faults, which is what we looked at last week. Okay, they can also be caused by eruptions, so volcanic eruptions. They can also be caused by landslides, meteor impacts, or nuclear detonations. Okay, so these are some of the ways we can get earthquakes, but they are mostly caused because we have some fault activity. Okay, so this is a quick review on last week. We looked at faults, what they are. They're planar breaks in the crust. Okay, so this is what a typical fault looks like. Okay, this is a nice diagram of a normal fault. So here's a quick review on the different types of faults. Again, this is more for you than for me to talk about. This is a nice review from last week, so our different types of faults that we have. Okay, what does an earthquake look like? So this is the anatomy of an earthquake. This is a nice diagram showing you all of the components of an earthquake. Okay, and so if you look at this diagram here, we have a focus, or a hypocenter. This is the point within the earth where an earthquake rupture starts. Okay, so if you look at this diagram, you have this nice fault going through the crust right here. Okay, this point, the focus, is where the earthquake rupture begins. Okay, and if you follow this point up to the surface, we have an epicenter. And this is the point at the surface of the earth directly above the focus. Okay, so if you were to follow this focus line all the way up, this would be the epicenter. This is where it comes on the surface of the earth. Okay, the fault, this is where the fracture in the rocks of the crust, right? So this is what's causing the earthquake to happen, right? We have this fault plane where these rocks are slipping against each other, either up, down, or side to side. Okay, you have the two plates. Okay, it doesn't always have to be that two plates are up against each other, right? It can be a fault can happen within the same plate. Okay, but oftentimes they are associated with plate boundaries, right? So it is two plates up against each other. Okay, so that's the most common way that we can get earthquakes, are our plate boundaries. And then seismic waves. These are the waves that transmit the energy released by an earthquake. Okay, so refer to this diagram for the anatomy of an earthquake. Okay, and so I'm not going to really go over this because I just showed it, right? So what happens during an earthquake, you're releasing a bunch of energy that was stored in the rocks by friction. Okay, and so one way to think about an earthquake, and we could do this as an experiment one day, but if you have a block, let's say a brick, right? And the brick is on a piece of wood with sandpaper on it. And you have the block, and you can look at this diagram here. It shows it quite nicely, right? You have a block, right? And this is a piece of wood. Maybe there's a bit of sandpaper, right? So you're creating friction. And then you attach a spring or a string to the block, right? And if you pull that block across the sandpaper, there's going to be friction underneath the block, right? And you're stretching the spring, Eventually, that friction is going to exceed its threshold and it's going to slip along this frictional surface here, right? And that would be your earthquake. Okay, so you're exceeding the amount of friction that a rock experiences. Okay, so you're going past that threshold, and that's what's causing the earthquake or the slip to happen, right? So you can think about a spring attached to a brick or a block of wood sliding over a really high friction surface such as sandpaper. Okay, that spring is going to only stretch so much before that block moves. Okay, you can also think of this as a vise with a clamp. You have a rock. One clamp is directing the rock in one direction and one in the other. Eventually, the rock is going to have some small elastic bending, then a fault, then the rock is going to break completely. And this is where we have our earthquake. Okay, again, just some more diagrams on that. Okay, keep it moving. Okay, again, just some more anatomies of earthquakes. Okay, you have the focus and the epicenter. Okay, so one neat thing about, okay, this is a good place for my head. One cool thing about earthquakes is that you can measure the amount of displacement across the fault. And this is really only works with a strike-slip fault, right? So you have two plates that are sliding past one another like so. Okay, and if you look at these diagram here, this is on the San Andreas Fault boundary. I think I showed this picture once or twice in class before, and it's a fence that's been offset by the San Andreas Fault, right? And so you can think that this fence was once upon a time connected, right? Why would you build a fence so far apart from each other like that? That doesn't quite make sense, right? Well, the fault displaced it. Okay, so the fault actually ripped right through this fence, pulling the fence this way, so in this direction, right? So this is the original fence, and then this part of the fence was moved or dragged by the fault. So I drew a little picture here of some mountains, okay? And you can imagine that the fault is ripping through this mountain zone. So you can imagine these two plates ripping this mountain range right in half, right? You can go and look at these mountains and figure out how far that fault displaced this mountain range. So you can look at the distance in between those two mountain ranges to figure out how much the fault moved. Okay, so we'll be talking about the displacement or offset of a fault, and that's what it means. How much has the fault moved, and how can we measure it? Okay, so whether it's through these markers like a fence, we can also use streams, so streams can get displaced by faults. Mountain chains are a really good way we can look at fault displacement. Okay, but that's what this means when we're talking about displacement or fault offset. Okay, it's measuring how much the fault has moved. Okay, seismographs. These are instruments that record ground motion. So this is how we can detect earthquakes. Okay, back in the day, they used a pen, a weight, and a piece of paper, and it actually recorded the movement of the earthquake based on the ground motion. Now we have some more sophisticated measures to measure seismic waves or earthquakes. Okay, this is a modern seismograph. used with a magnet and electric coil, and they're able to detect very small movements in the ground. Okay, so these are the data collectors. And these are read with a seismogram. So the data that is recorded by a seismograph, okay, and you can see, keep having to move my face around, all of these squiggles. This is recording all of the different seismic waves that an earthquake produces. Okay, and we'll go through the different seismic waves that the earthquake produces. Okay, seismic wave, again, really briefly, they're vibrations caused by the earthquake, and they travel in all directions from the focus, right? And the focus is where the earthquake is happening. Okay, so that you can imagine dropping a pebble into a body of water, right? You have this ripple as the displacement of the water is felt through you're dropping a rock or a stone into the water, right? You have these ripples forming from that motion, right? You can imagine that happening also with seismic waves, right? You have this release of energy in the ground. You're going to have these vibrations coming out in all radial directions of that earthquake. Okay, and we'll have different types of seismic waves or releases of energy. Okay, and we'll go through each of those really quickly. Okay, so remember, they travel in all directions from the focus. We have, there we go, my goodness. I'll put it there. Okay, so the first type of waves or seismic waves that we have that an earthquake produces are called P waves. Okay, and these this type of seismic energy travels through all types of materials, so solids, liquids, gases, right? So remember that the Earth is not just this one solid block of rock, right? There's mostly solid, but there's also groundwater. There's different types of sediment, so we can have bedrock, we can have soil, right? So materials that are kind of in the middle between rock and liquid. We also have gases, right? There's natural gases that are in our earth. That's what we use for energy, right? So there's different types of materials within our earth, and the P waves travel through all of these. Okay, so and they also travel the fastest. So they're going through all of these different types of materials that are in our earth, and they're traveling very fast. And one way you can think about P waves is a spring or a slinky, right? You're pulling that spring apart, right? So kind of like this elongation direction. Okay, so those are your P waves. And they also travel pretty deep. So they travel 6 or more kilometers into the crust. So they're pretty deep. They also travel very fast. The second waves to arrive are the S waves. And you can think of pulling a rope really taut and then kind of whipping it. It produces this wavelength through the rope. That's analogous to our S waves, and they travel a little bit shallower, so about 4 kilometers in the crust, and they're slower than P waves, so they're going to arrive after the P waves arrive. So when I mean arrive, right, we have these seismograms set up at different stations in our country, across the globe, right, and these waves are going to travel to these seismograms from the earthquake, right? And so when a seismogram is recording these seismic waves, so if we go back just a little bit, right, here's a nice seismogram here. It's going to record the different types of waves that the earthquake is producing, right? So the first wavelength that we see in the seismogram are our P waves, right? Those are the first types of seismic energy that the seismogram is going to record. Then after some time, the earthquake is going to produce these S waves, and that's going to be felt a little bit after these P waves are felt at the seismogram, right? So these are our second sets of wavelengths in our seismogram. Then the last wavelengths that the seismogram records are these surface wavelengths. Okay, so there's three different types of energy that the seismogram records, and these wavelengths are felt at different times, depending on how fast these are traveling and how large of an earthquake we're dealing with. Okay, so that's just a little backtrack there. Okay, so we have our P waves traveling first, our S waves arriving second, and then we have our surface waves. And these are the slowest types of waves that we get in an earthquake. Two different types of surface waves are L waves or love waves, and these are the S waves that intersect the land surface. Okay, so you can see this kind of back and forth motion that produces the L waves. The R waves are the P waves that intersect a land surface, and they cause the ground to ripple up and down like water. So you can see this kind of churning motion here produced by the R waves. Okay, so we have different types of seismic waves traveling through the crust and the rocks, and these are our three different types of wavelengths. Okay, so here's a nice synthesis of all of these different types of wavelengths. I won't go through them, but this is a nice summary of all of them, showing you the different types of motion that accommodate these different seismic waves, right? So we have our P waves, where we have a vibration direction going up and down. We have our S waves, producing this back and forth vibrating direction. This is also the most damaging wavelength produced by an earthquake. Then we have surface waves with our L and our R waves, and you can see the different types of motion that these produce in the earthquake, right? So we have different types of ground shaking, which are because there are different types of seismic waves being produced by our earthquakes. Okay, so how do we determine the location of an earthquake? So I mentioned that we have all of these seismograms set up throughout our country. So here's a bunch of our seismic networks that we have in our country. I'm sure there's more than these red triangles, but here's some of our network stations. Okay, and how this works is all of these seismograms are collecting this data, right? So when an earthquake goes off, all of these seismograms that can feel the earthquake are recording the data, right? So if you have an earthquake that happens on our west coast, the seismic waves are probably not going to travel to our east coast, right? So these seismograms on the east coast probably won't record any of the data felt by our west coast earthquakes unless they're pretty significant, right? If they are and it picks it up, then the ones on the east coast will record it as well, right? But let's say we have an earthquake happening right here in this kind of general area on the western side of the country, right? Different types of seismograms will pick up this energy that this earthquake outputs, right? And then you can plot these locations on a graph. Okay, so back here, we have these different wavelengths, right? These wavelengths are going to tell us how far away the earthquake is, depending on what seismogram you're looking at, right? So we have these different collection points here on the map, and you see these different circles, right? So each one of these recorders is recording all of the seismic data, right? And if you plot them up, their radius, so how far the earthquake is traveling, right? You can create a radius circle around the collector. Where that earthquake has actually happened, where it's actually has slipped, is going to be the intersection of the different circles that you're using, right? So each one of these seismograms picked up some energy, right? Depending on how far away it is going to depend on how big your circle is. To pinpoint the exact location of where the earthquake is happening, you look at the intersection of all three of these circles. So right in this general area here, that's going to be the intersection of all of these different data points. And that's where our earthquake is where our earthquake has slipped. Okay, so there's a couple of questions on that I already answered. Okay, so moving forward, we have a nice summary diagram on earthquakes, plate tectonics, and the different types of waves that we experience, our seismic waves, when we have an earthquake. So this is a really nice diagram to refer back to when you're looking at earthquakes. There we go. Okay, so how do we determine where these earthquakes are happening? So again, earthquakes, as we all know by now, are happening along these plate boundaries, right? So we can record plate boundary movement by GPS, right? We can also record plate movement and earthquake motion by displacement. So referring back to this diagram here, we can look at different rock bodies or different structures that have been moved by the fault, and we can assess their movement based on the displacement or the offset of these faults. Okay, I'm just going to flip through. This is a review on plate boundaries. I think we're all pretty much caught up on the fact that earthquakes are going to happen along plate boundaries. Okay, that's where they're going to happen. Okay, so this is really a review for everybody. We have convergent boundaries where we have shallow earthquakes happening here, and we also have really intermediate to deep earthquakes happening. Okay, and that earthquake zone is referred to is the Wadati-Benioff zone. Okay, so this is the earthquake zone happening in subduction zones. Okay, so you can think of earthquakes happening all along the subducting slab of this convergent boundary. There's a name for that. Okay, and this is where we have our intermediate to deep earthquakes happening in convergent boundaries. We have divergent boundaries, right? These are going to produce our normal faults, which are also going to cause some earthquakes. Again, these are going to be shallower, but they're going to happen, right? Because we do have faulting, we do have releasing of energy when we have that faulting. So we have divergent boundaries creating shallow earthquakes. Then we have transform plate boundaries. Now, these plate boundaries produce pretty moderate earthquakes. Some are shallow, some are moderate. Rarely are they ever deep, but they are a big deal because when they occur on land, they are very destructive. Okay, so our San Andreas Fault, a large portion of it is on land, right? It cuts right through California. Okay, so that's a big deal because we have a lot of people living in California. So when that earthquake ruptures, it's going to be felt by a lot of people. Okay, usually transform plate boundaries most of the time are in the middle of the ocean, so they're not a huge deal, but where they come and cut on land, they can be pretty significant and pretty deadly. Okay, so we also have intraplate earthquakes. This is about 5% of the earthquakes, and they are not near plate boundaries. Okay, and so these happen with remnant crustal weakness in failed rift or shear zones. Okay, so we all know by now that different parts of the earth experience different types of tectonic activity through time. Okay, so in different parts of the world, we might be in the middle of a continent, say the middle of the United States, Missouri, Arkansas, Tennessee, Kentucky, not quite the middle, but central enough. They have earthquakes there. There was actually a magnitude 7.0 earthquake in New Madrid, Missouri that was felt in 1811. This happened because there is remnant crustal weakness in these failed rift zones. Okay, so at one point in time, this area was experiencing rifting, right, which created a weak zone in the crust, right? Maybe there's some normal faults, ancient faults that are in this area. Now, there's really no plate boundary even close to this area, but faults are being felt because of this zone of weakness in the crust. Okay, so these earthquakes do happen, not accounting plate boundaries, but they're a lot rarer and about 5% of the earthquakes. Okay, I'll encourage you to go and look at these two links here. This is earthquakes in 3D visualization. So you have convergent and divergent boundaries, showing you what these earthquakes look like in 3D, and they're really, really neat. So I encourage you, there are a few minutes, just a visual, just to look at what these earthquakes look like on the globe. Okay, just a little bit more about last week. Okay, so let's look at earthquakes in the United States. Okay, so we all know that we have one plate boundary on one part of our country. Okay, and as we all know, that's going to be our west coast, right? So our west coast is experiencing some plate tectonic motion, right? We have a transform plate boundary in California. We also have a convergent boundary in our northwest corner, as well as in Alaska. So this region of the United States is experiencing some tectonic activity, right? Because it's a plate boundary or two plate boundaries. If you look at our East Coast, there's not a whole lot going on except for this New Madrid area, which we just talked about. Okay, and why is that? Why don't we have earthquakes on the East Coast? Because it's a passive margin. Okay, and just a review as to what a passive margin means, it's an area that is not experiencing any tectonic activity because it's not a plate boundary. Okay, so this plate, this North American plate, does not end here at our north or at our eastern boundary, right? Our plate keeps going and keeps extending out into the Atlantic Ocean where we have a divergent boundary. Okay, at the edge of our plate is where we're going to experience our earthquakes and our tectonic activity. But here on the eastern portion of the United States, we're not going to have earthquakes. We're not going to have tectonic activity because it's not a plate boundary. It's a passive margin. Okay, so it's the edge of our continent, right? Not the edge of our crust, not the edge of our plate, I should say. Okay, and so this is where we get all of our earthquakes, right? So mostly on the west coast, definitely in Alaska, but we do have a small pocket of intraplate earthquakes happening. Oh, and if we go back, we see Puerto Rico. Puerto Rico is on a plate boundary as well, and they're experiencing tons of earthquakes currently. Okay, so we have the San Andreas Fault, probably the most well-known transform plate boundary transform fault in the world. Okay, we have earthquakes in Alaska. Okay, we actually have tons of earthquakes in Alaska all the time. One of the biggest earthquakes ever felt, not the biggest, but one of them, was in Alaska, and it was in the 1960s. And it wasn't a big deal because most of Alaska is really remote, and people don't really live there. Oh, here we go. This is a cool diagram. I didn't even notice this. 1964, the earthquake, second largest ever recorded in the world. Okay, so that's pretty significant. The reason why it's not such a big deal, or why people don't really know about it too much, is because nobody lives there. Okay, so this big giant earthquake happened in the 1960s, but it wasn't a huge deal because this part of the world is so remote that people don't live there. Okay, so recognizing that these big earthquakes can happen, and they do happen all the time, but sometimes they're in parts of the world that are not as populated as others. Okay, so that's a big deal. And that's a big reason why we look at some earthquakes more than others, right? So the San Andreas Fault is a pretty significant fault, and it won't produce the biggest earthquake in the world. Okay, so if that earthquake, if that fault ruptures, it's not going to be a huge magnitude earthquake happening, but it's going to be a big deal because there are millions and millions of people that live in California, and they will absolutely be impacted by that fault rupture. Okay, but some of the biggest earthquakes in the world are happening in these remote areas, and people don't care. So that's something to keep in mind when you're thinking about these hazardous areas. Okay, so we talked about the New Madrid seismic zone. This is our interplate earthquakes. Okay, and you can see the bedrock that's causing these earthquakes, right? This ancient failed rifting zone here. Okay, some of the most recent devastating earthquakes. This is a nice diagram showing where these the world's largest earthquakes have happened since 1900, and this hasn't been updated. There was some pretty significant earthquakes that have recently happened in Mexico, Puerto Rico. Okay, but if you notice, they are all pretty much on these convergent boundaries here. So Alaska, we have South America, we have these parts in the Pacific Ocean, Japan, some Eastern Asian countries. These are all convergent boundaries. These are all our world's largest earthquakes. Okay, again, this is another diagram. Okay, so earthquake hazards. This is these are screenshots of the movie San Andreas with The Rock. I recommend it. It is good fun, but it is absolutely inaccurate on many levels. Okay, but here's some spoilers on what that looks like. Okay, so what are the earthquake hazards associated with earthquakes? The first one is an obvious ground shaking. Okay, so material like soil, sediment, these all respond to seismic waves differently. Okay, the harder the rock, okay, here's a nice diagram. The harder the rock, the less intense the earthquake will feel, okay, because the rock is going to absorb those seismic waves. So if you have a building on solid bedrock, it's not going to experience as much shaking and ground motion as you would if you had a house on poorly consolidated sediment. Okay, those seismic waves are going to go through that unconsolidated sediment and shake it around, right, and jumble it up, right, because it's not a solid consolidated rock. That sediment is going to feel that energy a lot greater than the solid bedrock would, right? So these homes that are on this poorly consolidated sediment are going to experience a lot more damage than these houses on the solid rock. Okay, so the looser the material is, the more damage you will feel on these earthquakes. Okay, landslides. Okay, this is something that's also pretty intuitive to happen with earthquakes, right? You shake the ground, you shake the rocks, you're going to cause a bunch of landslides, debris flows, rock falls, avalanches, right? This is when we have slope failure. Okay, so you have mountains, you have hills, you have any different types of slopes can fail or they can slide. Another word for fail is slide when you have these earthquakes. Okay, so this is something also extremely common in earthquakes. This is a highway in Taiwan, I believe, that had this pretty huge landslide happened after an earthquake. Okay, and this is slope failure. Okay, so the slope fails and you have this really huge landslide. Okay, another cool one, I guess it's not really cool when you're in it, but I like to talk about liquefaction. Okay, so remember I just talked about different types of rock and sediment experiencing these seismic waves differently. Well, if you have a unconsolidated sediment, usually soil that has some type of saturation to it, so usually water-filled sediments, when you shake that in an earthquake, when you shake that material, it starts to form a type of slurry or like a concrete, and it becomes like a quicksand. So you can see this car has been eaten by the road. It looks like a road, but it's actually this really poorly consolidated clay type of material. And when an earthquake went through this area, that material mixed in with the water, creating this slurry, and totally ate the car. Okay, so this is what is called liquefaction. Okay, so when you have this unconsolidated sediment and it's experiencing this earthquake, okay, it'll turn into this slurry type of material. Tsunamis. Okay, tsunamis, there's a picture of the tsunami. I think that was in Indonesia. This is another really common earthquake hazard with tsunamis, but one thing I want to stress is that these tsunamis are only really going to happen in one type of plate boundary, and that's our convergent plate boundary. Okay, and tsunamis are a result from a displacement, usually in the seafloor, by an earthquake. Tsunamis can also happen in volcanic explosions. I'll talk about that more in the next couple of lectures. But one really common way, the most common way that we get tsunamis is through these earthquakes. And they're most common in these subduction zone settings. Okay, and I think I have a couple more slides on this. These waves are unrelated to wind. They can travel several hundreds of kilometers per hour, and they travel as a raised plateau that pours onto the land. So you can see this huge wall of water. That's really what a tsunami is this wall. Not so much a huge wave as we can think, but more like a huge wall of water that's just charging towards land. Okay, and here's some diagrams of how these form, right? So we have a fault being produced in the middle of the ocean. It's displacing a large amount of water, sometimes rock, and that water has to go somewhere. Okay, so you can see this big wall of water starting to travel towards the land. Okay, and as it moves closer to land, right, the beach or the slope is going to get shallower and shallower and shallower. Okay, and so the wave is going to get bigger as the water gets shallower. So it'll usually start off as this kind of hump in the water, and as it travels towards land, that hump is going to get bigger and bigger as the water gets shallower, where finally it gets to the beach and that wall of water washes onto shore, pretty much decimating anything in its path. Okay, some more diagrams. Here's a nice comparison of wind waves versus tsunami waves. Okay, another geohazard associated with earthquakes is fires. Okay, so this is common in earthquakes. The shaking topples stoves, candles, but it also breaks power lines, gas mains, infrastructure. So a lot of these fires that you're seeing here are really gas line breaks, right? We all use natural gas, or most of us do, to power our homes in various ways. When our infrastructure is broken by earthquakes, it can create really deadly fires. And then our last one that we can talk about is disease. Okay, so in poorer parts of the countries, when we have these earthquakes happening, totally decimating structures that are not as modern as they should be in these earthquake-prone areas, right? The buildings crumble and collapse pretty easily. Sanitation is non-existent because everything is pretty much decimated. Hospitals may be destroyed, etc. Health professionals overwhelmed. This is an easy start to disease is when these earthquakes happening. Okay, this is a chart. Again, these charts have not been updated in recent years. There's definitely been some pretty significant earthquakes that have happened in the past, I guess 2011, so almost 10 years. So these need to be updated. But these are some pretty significant earthquakes that have happened, and it shows you how many people died with these earthquakes. So one of the last, most recent ones in this chart, Japan, there was a large earthquake that happened, and it also caused a tsunami, right? And that resulted in 20,000 deaths. Haiti, back in 2010, 230,000 people died. So these earthquakes cause mass destruction, and very many fatalities can happen. Okay, so I won't go through all of these, but these are some examples of some of the recent devastating earthquakes that we've had. This particular one on this slide occurred in the Indian Ocean, and it caused a tsunami in Indonesia, killing very many people. 250,000 people died, which is insane and awful. And here are some pictures of what that looked like. This is taken right before the tsunami hit. You can see the water is receding, so it's being pulled back into the ocean. This is usually what happens right before a tsunami hits. You'll see the water recede and the beach almost being wiped away of water, right? The water is being sucked out. into the ocean because it's experienced this displacement of energy and water. And a few moments later, a tsunami will have hit. All of these people that you're seeing here on the beach ended up surviving, which is very lucky. But they were there when the tsunami hit, exploring the beach as the water receded. Okay, before and after. Some terrible devastation in Japan in 2011. Okay, and I won't go through all of these. Okay, this is a slide showing tsunami detectors. So there are ways that we can detect tsunamis as they're about to happen. These sense pressure increases from changes in the ocean. These can save thousands of lives. It's very hard to predict tsunamis, but we do have these few measurements, these few devices that we can use, and this is one of them in the Pacific Ocean. Okay, so getting towards the end, I hope. How are earthquakes measured? So there's two ways we can measure earthquakes, intensity and magnitude. Okay, and intensity is the damage observed in the field. Okay, so that's, and I'll go through these actually one by one. And magnitude is the amount of ground motion measured on a seismograph. Okay, so that's intensity and magnitude. I'll go through really quick. Okay, so magnitude, whoops. This is the standard measure of the shaking and energy released recorded on a seismogram. Intensity is the measure of the effects on the people in the building. So how much damage? Did your bed move up and down? Did your plates fall off of a shelf? That kind of thing. That's intensity, how it affects the people in the buildings. This is an earthquake intensity chart. So you can read this on your own time, but extreme intensity, few, if any, masonry structures remain standing. So this is all based on damage. Okay, so how humans, how buildings, how structures feel the earthquake. Okay, here's some different types of intensity. Okay, and then magnitude. This is measured on a logarithmic scale. So each division is a tenfold of the one before. So you can imagine that these earthquakes, the difference between a 7 magnitude versus an 8 magnitude is 10 times the amount of energy felt. Okay, so magnitude is described using different scales. So you can see the different scales. The Richter scale is best for local measurements. The surface scale, based on the R motions in shallow earthquakes, body wave scales. The magnitude that we usually use when we're talking about earthquakes, magnitude 7 versus 8. This is from the moment magnitude scale, and this is the best measurement, and it's based on characteristics of different seismic waves in the area of displacement. So it's taking into consideration displacement of the fault slip. So again, how far the fault has moved and displaced the rock or the area, and the different seismic wave measurements recorded in the seismograph. Okay, so a couple of other diagrams on that. Okay, this is a cool diagram showing you the amount of energy equivalents. Okay, so there was, let's see, a moderate earthquake with property damage. Okay, so this is a magnitude 6 earthquake. Okay, this has a little bit less of an energy equivalent as the Hiroshima atomic bomb. So you can imagine that these larger earthquakes, such as a magnitude 8 or so, is equivalent to the world's largest nuclear test or a Mount St. Helens eruption, right? So the amount of energy that's being released in these earthquakes is incredible. So you can look at these energy equivalents to see the different types of magnitudes and how much energy is equivalent to that in different measurements: tornadoes, bombs, lightning bolts, etc. So that's a pretty neat diagram. Okay, so earthquake predictions. How do we know? How do we predict them? Short answer, it's very, very difficult. So one of the ways we can look at earthquake prediction is by looking at the rock record. Okay, so looking at the ancient rocks and looking at different faults, looking at their offset here, and trying to piece together when these earthquakes might have happened based on the age of the rocks. So radiometric dating can tell us how old the rocks are, and if you have some faults along those rock layers, you can estimate roughly when these earthquakes happened. A very rough estimate, but it's one of the ways we can figure out when these ancient earthquakes ruptured. Okay, and so these are more of our long-term predictions. Usually, predictions are based on recurrence intervals, so we can only really work with the data that we have. Okay, so if we have 100 years of earthquake data, which is what we mostly have, I think less than 100 years, right? We can kind of estimate when the next earthquake in a specific area will be based on the data that we have. So we are really limited to how much we can predict because the data might not be there. So there might be one part of the world that hasn't had an earthquake in a long time, but has historically had very many earthquakes, right? But our data that we have available is not available for that area, right? Because our seismograms are pretty recent instruments, so we can only go off based on the data that we can collect, right? And based on that data, we can predict when the next earthquakes will happen. But this is all based on the data that's available. So that's a huge limiting factor into how we can predict earthquakes and where we can assess where these geohazards will be. Okay. Short-term predictions are pretty much impossible. So we can't really predict earthquakes that are going to happen in the next weeks or even months. But we can predict when an earthquake might happen in the next 100 years or so. So we all know that California, everyone says the big one's going to come, the big one's going to come. That's all based on earthquake data that we have collected from over the years, right? So we're predicting that California is going to experience a big earthquake, which can happen at any point from now in the next 50 or 100 years. Okay, but these are all loose predictions based on the data that we have that we were able to collect. Okay, and so how do we prepare for these earthquakes? These new buildings are being built across the world that are in earthquake-prone areas that really accommodate ground motion. Okay, so masonry buildings, brick and mortars, these are types of buildings that are usually pretty bad in earthquakes, right? They have a foundation, maybe in bedrock, maybe it's not, but when the ground shaking is felt in these buildings, they're pretty easy to topple because they can't accommodate ground motion or the swaying of the ground beneath it, right? So you have these different buildings, usually from the 1980s and more recent, that are more earthquake prone to stand. So one of my favorite examples is Taipei 101. And this was the world's tallest building from 2004 through 2010. Okay, it's 101 floors, about 1,700 feet tall. It's home to the world's tallest Starbucks on the 35th floor. It's in the country of Taiwan. If you don't know where Taiwan is, it's a small country off of mainland China. It's not part of China, but it is very close. Oh, here's a nice picture of that. So here's Taiwan in the middle of the Pacific, and here's mainland China. Okay, so that's where Taiwan is, and you can see on this diagram here that it's actually the location of a double convergent boundary. So the Eurasian plate is actually subducting under the Philippine Sea plate in this area here. But there, for whatever reason, there could be a different type of density going on in these plates on the northern boundary. The Philippine Sea plate is actually subducting underneath the Eurasian plate. So it's kind of this weird thing where we have these two plates subducting underneath each other, just at different points. So it's a very funky plate boundary, and it cuts right through Taiwan. So you can imagine that this island experiences a large number of earthquakes. They experienced a really devastating one in 1999. Here's some pictures of it. About at least 2,000 people died in this earthquake. Okay, so it's a very earthquake-prone country. I actually was there last 2018, January. Is that 2 years ago? A year ago? Oh gosh, can't remember. A year ago. I was there, and I actually felt a small earthquake while I was there. So these earthquakes happen all the time. So how do you build one of the world's tallest buildings in the world in this really earthquake-prone country? And this building is actually really neat because there is an earthquake damper right towards the top of the building. This is actually in Spanish, this diagram. So a little cultural lesson for you all, if you can read that. This ball is basically this huge ball that dampens. It's called the dampener, and it's in the top of Taipei 101. And as the earthquake is felt in the building, this ball moves and shifts to balance the different types of swaying that this building will experience when an earthquake comes through. So this ball you will see, and these people are visiting Taipei 101 in this observatory. If an earthquake strikes, you can actually see the ball moving while you're there, which is scary, terrifying. There are videos of people being in Taipei 101 as this ball is moving because there is an earthquake that's happening. So click on these videos and watch a couple of them. That's actually all I have. So that's